Welcome to tonight's edition of Space Class. If you've never been here before, welcome. Space Class is a public astronomy talk series we've been running now for more than 2 years. And this month's edition of Space Class will be on the James Webb Space Telescope. Now, before we delve right in and introduce our speakers, there's a couple of rules of Space Class. As you know, Borderlands is right by train tracks, and so periodically trains will go by, at which point our speakers will interrupt themselves, raise their glasses of beer, which they will hopefully have, otherwise we will give it to them very shortly, and say choo choo, at which point please join them in taking a swig of beer. This also keeps the bartenders happy because you have to keep buying beer. The pizza, we're told, will be here shortly. We will have an intermission, so you will be able to go get those. But when it comes in October, we'll have to wait to come back there. Again, we also have features for sale. Please buy them. Everything that you go, give us goes to outreach for local schools. We don't make any money off of the stuff we do here. It's purely volunteer work. So this one's talk, as I said, is on the James Webb Space Telescope. Now, the University of Arizona has a huge involvement in the James Webb Space Telescope, with 2 professors on campus, George and Marcia Hickey, being principal investigators for 2 of the instruments that it will have. George and Marcia's right-hand people are Stacey and Fraine. Stacey got her PhD at UMass Amherst, while Jonathan got his from University of Maryland and College Park. They've both been working extensively on the testing and development of the instrument suite, and they'll be telling us all about their experiments here with James Webb. And without further ado, we'll let them take it off because rather than doing different talks, so just going to be going back and forth. So, Stacey.
Okay. Hi, everybody. And thank you for. I'm excited too. Yep. Thank you for coming to Space Tracks, and thanks for Borderlands for hosting. So my name is Stacey Alberts, and today Jonathan and I are going to be telling you about the James Webb Space Telescope. So Jonathan and I both work at Stewart Observatory over at the University of Arizona. And JWST is the next big thing in astronomy. It is an unparalleled infrared space telescope that's going to launch in 2018. And when it does, it's going to be the most powerful telescope in space. So today, we're going to tell you a bit about what makes JWST so special, and then we're going to tell you about our respective science. I work on galaxies. He's going to tell you about exoplanets. And as you can see, those are 2 of the main goals of JWST that are listed up here. Okay, so JWST is a true next-generation telescope, building on the successes of the Hubble Space Telescope and then pushing out into new frontiers. What makes James Webb special can be summed up into 3 things. It's bigger, it's redder, and it's colder. So what do we mean by that? Well, when we talk about how big a telescope is, we're usually talking about how big its primary mirror is. So over here, we see the Hubble primary mirror, which is a respectable 2.4 meters in diameter. And then here we have the James Webb primary mirror. It is made up of 18 different segments that all work together to make one big mirror that is 6.5 meters in diameter. So what does that get us? Well, you can think of telescopes as kind of like light buckets. Point them at the sky and they collect photons. The bigger your bucket, the more photons you collect. So already, we're in good shape. But making a bigger telescope also gives you better resolution, or the ability to look at fine details of what you're looking at. So when we talk about the wavelengths that James Webb is going to look at in the infrared, and we'll talk about that later, when we compare them to existing facilities, such as the Spitzer Space Telescope, we see that the resolution is going to be much improved. We're going to see a lot more detail in the galaxies that we're looking at in the James Webb. So that's our telescope being bigger, and that's a great start, but it's also going to be redder. And what I mean about that is that when we compare to Hubble, Hubble primarily looks at shorter wavelengths. It started out with instruments in the ultraviolet and the visible, and then later added an instrument that got a little bit into the near infrared. So that's right here. James Webb is going to get all of these longer wavelengths over here, starting in the near infrared and going out to the mid infrared. Now we have existing facilities that look at infrared wavelengths already, such as the Spitzer Space Telescope, but as you can see from these comparison right here, which is to scale, Spitzer is tiny. James Webb is going to be huge, which is going to give us a great improvement. So how do we look at these infrared wavelengths? Well, a telescope needs instruments to look at different wavelengths. JWST has 4 because as astronomers, why would we want one instrument when we can have 4 instruments? So the 4 instruments on James Webb are the near-infrared camera, or NIRCam, the near-infrared spectrograph, or NIRSpec, the near-infrared imager and slitless spectrograph, or NIRIS, and the mid-infrared instrument, or MIRI. Now, these different instruments look at the infrared wavelengths in slightly different ways, in slightly different methods. And I'm not going to go into all the details except to say that each instrument has at least 3 modes, which means that James Webb has at least 12 different ways of taking data because we like to make life complicated for ourselves. I'm not going to explain them all to you because your heads would explode. But I will say that the University of Arizona is directly involved in 2 of the instruments. The near-infrared camera is P.I., that means she's the principal investigator, by Dr. Marcia Ricci here at the university. So all of the good stuff going on with NIRCam is happening here. And the mid-infrared instrument is a joint collaboration between NASA and Europe. And on the NASA side, the US side, we are leading up the science effort for MIRI here in Arizona. So there's a lot of awesome stuff going on here for James Webb. Okay, so our telescope is bigger and redder. It also needs to be colder. It needs to be really, really cold, in fact. And the reason is that once you start getting to the infrared wavelengths, you start to pick up on things that have heat. Because anything that has heat, has thermal energy, is emitting in the infrared. So this is really, really bad. And my boss likes to say that doing thermal infrared astronomy from the ground is like finding a match in a blast furnace. I don't see the match. I don't know if you do. So one way we get around this is we put our telescope in space. Once we put it in space, all of this junk right here, all that signal that's contaminating our telescope, it's gone. We instantly get a really good improvement. But it turns out that that's still not good enough. Okay? We need to get away from the Earth entirely. So you probably, maybe you know, that the Hubble Space Telescope orbits around the Earth. But we're not going to put James Webb around the Earth. We're going to put it all the way over here, 1 million miles away at L2. L2 is a point that orbits around the Sun, with the Earth in between it. And when we come out here, we're going to be even colder. But that is still, in fact, not good enough. We need to be colder. So we built ourselves a sun shield. This is a sun shield. It is the size of a tennis court, and you can tell because that's a person standing right there inside of it. So the sun shield gets put on the back of the telescope right here. This is the sun shield. Here's your mirror. Your instruments go on the back. That's the mirror part. And then this sun shield is always between the sun and the mirror and the instruments. So James Webb is going to have a hot side and a cold side. The hot side gets pretty toasty, 185 degrees Fahrenheit. The cold side is down at negative 388 degrees Fahrenheit, or 40 Kelvin. That is cold. However, still not good enough. It turns out that when you go even farther into the wavelengths, so here we're getting longer wavelengths, you pick up on even more contamination. So we need to be even colder if we want to go out here in the longer wavelengths. So 3 of the instruments don't care, but the mid-infrared instrument goes all the way over here to these longer wavelengths, and so it needs to be even colder. So we built it a refrigerator. And I'm not even joking, this is kind of like a really advanced refrigerator. So this is the MIRI cryo cooler. It's going to take helium gas and recycle it around to cool down the instrument. And then when it does, MIRI is going to be a mere 7 degrees Kelvin. That is 7 degrees above absolute zero. That's cold, and now we're in business. So combining these 3 things, James Webb is bigger, it's redder, it's colder, and that means that it can see farther and fainter objects than we've ever seen before. All right. So that's what makes James Webb special. Now we're going to tell you a little bit about where it's at, and I'm going to turn over the floor to Jonathan.
at the moment is located in the Goddard Space Flight Center. That's just outside of DC in Maryland. And you can see here is what they're doing is they're putting together those 18 gold segments that we showed you before. And each one of these little bins here will hold a segment, I think it's about a meter wide each, or half a meter wide each. And so the idea that I wanted to show here is, see how fast these people are moving? They're not that fast. That's not how NASA scientists work. But what is awesome is that this entire machine here takes about a day to work. And so to go from here over in the corner, where they open up the black casing and they test the gold mirror to make sure everything's working great. And then they put it back on the black mirror, case back on there. And then they lift it up with an awesome advanced NASA crane, basically. And then place it over, I think, here. Yeah. And then to go from here to there takes about an hour. To go from this platform into the actual placement could take the rest of the day, because they have to get it down to the precision of microns. They're moving at, I believe, like sub-microns per second, just to get it moving around. And the idea for that is that the better the alignment they have placing the mirrors in there, the better everything else works. And so the great part is that they're able to do that, and they're able to get it very nicely finished. And sometime in February of this year, they were actually got it placed in all the different mirror segments. So we've got, yeah. So here is after they're done with that, after all the assembly was done, they then of course test it to make sure. Well, I think testing was a bit of a misnomer. They have to then take pictures of it because it's pretty. And so, and in fact, some of the NASA high ups flew to Goddard to take pictures in the gold mirror. So our first trivia question, and I have to announce, to answer the trivia question to get the prize, right? Okay. You have to raise your hand and be called on, because yelling the answers out doesn't help anybody. All right, the first trivia question is, how much gold do you think is on the mirrors themselves, all 18 mirrors? Is it in ounces, pounds, tons, what number? I didn't hear you. Ounces, sure, okay. How many ounces? 8 ounces, awesome. That's a close answer, by the way. Anybody else want to throw it out there?
She's got 1 ounce.
Okay.
1 ounce.
1 ounce, exactly. The answer is 1 ounce. On all 18 mirror segments, they use this awesome, I think it's called vapor deposition, awesome method where they just let the gold literally float down onto the telescope. And they're able to coat them a micron thick. And so in the end, it looks like a giant piece of gold, but that's just highly reflective and very expertly designed. But in the end, it's actually less gold than in anybody's wedding. It's an amazingly small amount of gold, which is, the telescope costs a lot of money, but that's not why. Lastly, where does all the money go? Tell me how much it costs right now? Okay. Now, it's in the billions of dollars, like $8 or $9 billion so far. And about half, that's the total. Okay, so by launch it'll be about $9 billion, and half of that went into testing. Because what happened with the previous major space telescopes, they cost billions of dollars, not 9, maybe 1, even half $500 million. And when they got into space, then we started testing, and we found errors, and those errors build up, and we have to fix them. Granted, they're not huge, except for, of course, HSD has to have a lens correction like my glasses. But at the same time, if we put all the money in now into testing it, then by the time launch happens, by the time the first images come through, we're good. We can almost expect all of the problems to be known before the science comes in, so the first science gets done, and it's good science. So that's actually where Stacey and I both came in. Here, this testing, what they're doing is in a centrifuge, because who doesn't want to take $4 billion to put it in the centrifuge? And so what happened, we have to make sure that they can withstand the G-forces of a rocket. And the way you do that, the way that astronauts do that, the way that jet fighters do, pilots do that, is they can sit in a centrifuge. And that's exactly what we do with our instruments, make sure they can withstand the principal force going through the rocket ejection from Earth. Second, one of the big tests that our team does is we actually went to Goddard Space Flight Center, where they took all the instruments and sat them in a cryogenic vacuum, and this was the third test, so it's CV3, Cryovac Test 3, where we then shot all kinds of expected scientifically valid test data to try to understand what's going to happen on the first day. Do you want to? not really an analogy at all, but so you want to make sure that you know all the problems before it gets into space, and this is how we do it, by putting it in a giant vacuum. Now that was in Goddard, and we were testing almost 6 months straight, and as a result, some of us, Stacey, got stuck in the snow.
So I don't know if anybody was in DC in January or saw it on the news, but basically there was this big blizzard and the entire region just shut down. I mean, the blizzard started, the roads were shut down, businesses were shut down, the subway was shut down, nobody went outside except for us. Because it turns out that while you're doing this testing, you're spending a lot of money. Every time the instruments are in the cryovac chamber, and we can't just take them in and out, that's money, that's time. This is 24/7 testing, and we're on a schedule, and we're spending money. So a bunch of volunteers, scientists, and engineers were like, all right, we are going to do this in a blizzard. So we made some preparations. We put some beds in some offices. We put some signs up to tell everybody to shut up because people were sleeping. And somebody, I still don't know who, bought a bunch of Hormel chili. I don't think it was actually eaten. All right. So, but it was all worth it in the end. Oh, and just to tell you how dedicated, one of our guys got up at like 7 in the morning and walked 2 miles from his hotel to the place during the blizzard to make his shift. So we're a little crazy, but it pays off because we finished. The primary mirror was assembled in February, cryovac-free testing wrapped in spring of 2016. The instruments have been integrated onto the telescope, they go on the back. And Houston, we have a telescope. So the next step is to ship it all to Johnson Space Flight Center in Houston, which is why that joke works. And then it goes through some more testing, because we like testing, and then...
So then we have to put it actually in the spacecraft. The question always comes up, and did you come up with this slide?
No, that's George.
Okay, so George Ricky came up with the P.I. the Mirror mission came up with how do you get a telescope in a spacecraft? Option 1, you hire a giant gorilla named King Kong to just shove it in there. You open up the cavity and just put it in, but he was busy. So you should know that the telescope itself is, the previous telescope, the biggest one we had at the time was 44 feet long. The new one, James Webb, is 72 feet long, so like 50% bigger. And the Hubble took the biggest thing we had to fly it up there, so we have to come up with a bigger one, which I think is through, is it ESA? Yeah, it's ESA rocket. Yeah. Ariane 5 ESA rocket. And so to put the telescope in there, it doesn't fit because it's huge and it's awesome. It costs a lot of money. So what we ended up having to do is actually to fold it up into several different, not pieces, but several different contortion origami structures. In particular, you can see that there's, most of the mirror segments are here, but then there's 3 here and there's 3 on the other side as well. And on top of that, this little guy on top there is called a secondary mirror. It's very important for positioning the light into the actual instruments. And then behind it is where those off-film sun shields cool it down to almost 7 Kelvin. All of that has to fit inside the rocket, and that's not physically possible. We'll show you a video of how it all works later, shortly. But the idea is that you have to fold it up exactly right and perfectly fit inside the cavity, and then ship it down to French Guiana and fly there because ESA has a launch facility there. Now, our second trivia question is, why French Guiana? All right, I think on the right was the first hand up.
Because it's closer to the equator.
That is correct. Now, do you know why it's close to the equator matters?
Because it costs less fuel to do it.
Yep. So you get a little extra kick from the Earth. The Earth does a little help for you with the spin around the equator. It's a little bit faster than anywhere else that we have on the Earth. So ESA has friends, or probably owns French Guiana. And as a result, they built a space facility there, just like Kennedy, and we're able to launch from that location. So here, after launch, here's what's going to happen. So once it goes into space, once it goes into space, it'll deploy from the actual space shuttle and detract its solar shields. The first thing you need is power. And once you have the power, then all of the other systems can start to turn on piece by piece by piece. And if you notice a little timer up here, I was personally surprised exactly how long it takes for this little guy you'll see shortly to deploy. That's the radio antenna. So for approximately 1 whole day, NASA is crying, hoping that antenna deploys, and everything else too. But if we can communicate with it, we can probably fix everything else. If we can't communicate with it, goodbye. So a whole day before that deploys. And then next, as it says here, the forward shield something, which holds the sun shield out here, deploys, and the back one deploys. And those are carrying those awesome metallic structures that are going to reflect all the solar light, infrared light, and cool the telescope down. Now the giant structure at the top has to be separated from the main to the lower body, because even with all of these cooling devices we have, just putting physical distance between the mirroring instruments and the actual contact of the sun matters. It'll actually help us cool down to the desired temperature. And finally, and hopefully all this works exactly as you see it. There's not going to be any secondary telescope next to it to watch. And what's going to happen is the sun shield gets deployed and then tightened. And as it gets tightened, it pops up. And you see here there's 4 different membranes. So wait, you're right. It's five different membranes. She was right. Yeah, we had a little bit on that. 5 different membranes that go up there. I'll explain what that does in a minute, so you keep going. But yeah, it's basically a radiator. And ending up, the sun comes in on one side, and it heats up each layer of it separately so that the actual telescope is cool. And way cooler, there you go. That's what points the light from these gold mirrors into the shaft in the middle, into the instruments. That's the secondary mirror. So if the secondary mirror deploys correctly, then we're aligned. It's correctly, but let's just keep our thumbs crossed. So finally, of course, these side mirrors have to deploy, and you get all 18 segments together to get a 6-capita telescope. Now, before I worked for James Webb, I used to make this joke that James Webb is a variable 3 to 6 meter telescope, because if the mirrors don't deploy, you've only got 3 meters. It'll still work. A secondary mirror doesn't deploy, then we're in trouble. But in the end, you have here all 18 segments. The light comes in here, bounces off the secondary mirror, and goes into the instrument chassis in the back. Now, I'm personally fascinated by the sun shield configuration itself, so you get a short introduction to that. As the solar light comes in through the bottom, and it is mostly reflected off the first layer, but some of it's going to get absorbed, especially infrared. As a result, the bottom one there heats up. And then it radiates an infrared wavelength, which is exactly what we're looking at. So we need to block the infrared from the first shield to hit the second shield, the third, fourth, and fifth shield along. And cascading downwards, you get less and less and less contaminating photons into the actual instruments, which is a fabulous non-astrophysical awesomeness. My favorite part is the sun shield itself. So to carry on though, we'll go on to the actual science now and have Stacey come back.
All right, let's talk about science. Specifically, let's talk about galaxies. Okay, so just to remind you, the James Webb Space Telescope is sitting on the shoulders of the Hubble Space Telescope, the Spitzer Space Telescope, and tons of other space facilities and ground-based facilities that we've been working with for the last few decades. So the big questions that James Webb is going to answer are not so much the starting point when it comes to galaxies, but really getting into the meat of the issue and the details. So what we want to ask with James Webb is we want to ask first, what do the first galaxies look like? So Hubble has been able to peer back into the early universe, see what galaxies look like. We're going to look even farther, and I'm going to talk about that in a minute. What causes galaxies specifically to change over time? We know what galaxies look like nearby, we know what some of them look like farther away, but we don't know exactly how they get the shapes and the sizes that they do. What happens when galaxies collide? Sometimes they collide with each other, it's awesome, but what happens when they do? How do the black holes that we think are in all galaxies affect the galaxies that they're in? And lastly, how do we get all of the heavy elements that we know and love, because we're made of them, how do we get them to form and evolve, and what does that have to do with their host galaxies? So to answer these questions, we need to go back to the past, JWST. But first, let's look at what we already know. This is probably something that you've seen before. It's one of the most popular pictures to come out of Hubble. This is the Hubble Ultra Deep Field. So what happened here was we took Hubble and we pointed it at a small patch of the sky, and I mean small, there it is, compared to the moon. And we picked this patch of the sky because there was literally nothing interesting there. It was just, there was nothing, it was boring. So pointing Hubble here, we stared at it for about 11 days, and this is what we got. There are 10,000 objects in this image. Now, trivia question, how many of them are stars?
Zero.
I guess. Correct?
Zero.
Anybody else? No, one was already said. Yeah? 4. Does anybody know how we can tell? Zach?
Is it because of the diffraction spikes on a few of those?
It is indeed. So here we see diffraction spikes. That means that's a star. There's one more over here. There's one more over here, and the last one is tiny. You can probably see it on the screen. Of the 10,000 objects in this field, there are 4 stars. The rest are galaxies. All of them in this tiny bit of space that has nothing interesting in it. So what do we know about these galaxies then? Well, we've looked at a lot of galaxies that are nearby, and we've seen that they come in a lot of shapes and sizes, but they can largely be characterized into a couple different categories. So first we have elliptical and lenticular galaxies. These guys are very brown, they're kind of featureless. When we look at visible light, they're very red, and that's because they're not forming stars anymore. They're kind of like old systems that aren't really doing anything anymore. They're just hanging out. Over here, we have spiral galaxies. Now, spiral galaxies are like the Milky Way. They're kind of these disks that have these awesome spiral arms. And when we look at them with things like Hubble and the visible light, they're very blue. And that's because they are forming new stars. They have a lot of action going on. They are building up their stellar populations. And you can split spiral galaxies into 2 kinds, boring regular spiral galaxies and spiral galaxies with bars. I know all of you love bars, so. All right. So how do the galaxies get these shapes? To answer that, we need to look back in time. And the reason is that galaxies change over such a long time scale, millions and billions of years, that no one astronomer can just watch one galaxy and see how it changes. We don't live that long. So what we need to do is we need to take many snapshots in time of a lot of different galaxies to kind of piece together the puzzle of how they form and evolve. So we can do this by looking at things like the Hubble Ultra Deep Field and finding galaxies where we see the light from when the galaxy was young. And the reason that we can do this is because light travels at a finite speed, right? So if a galaxy is really far away from us, its light takes time to reach us. And so the light that we see coming off that galaxy may be billions and billions of years old by the time it reaches us. So we have these galaxies that were picked out of the Hubble Ultra Deep Field. They kind of follow the same sequence as what we were just looking at, except that they are all, when their light left those galaxies, it was 4 billion years ago. So we're seeing them at a different point in time. If we then go back farther and look at galaxies where their light left them 11 billion years ago, we see that again, we can put them into these categories, but they're kind of starting to look different. They look a little bit fuzzier, partially because they're just farther away and harder to see. But they also look very red. Oh, that's interesting. So, if we take the Hubble Ultra Deep Field and we wonder what it would look like with JWST, and then we go to somebody who makes simulations, we get this. This is a simulation of what the Hubble Ultra Deep Field will look like with James Webb. You can see that, again, we are getting thousands and thousands of galaxies. They're coming in all sorts of shapes and colors, and they actually kind of look a lot similar to what Hubble already saw. So why do we need James Webb? I don't know. It's bigger and redder. Okay, woo! All right. So to recap from beginning of the talk, bigger means a bigger bucket, more light collected. That's awesome. See fainter things. We can also get more fine details. But why do we care about redder when it comes to galaxies? Why do we want to look at the infrared instead of the visible light, like we've already looked at with Hubble? Well, a couple of reasons. Galaxies have dust, they have molecules, and they have old red stars. And these things all emit in the infrared. So we can use James Webb to get an entirely new set of information to go along with the information we've already gotten from Hubble. And to illustrate this, we're going to go back to the Milky Way, and we're going to look at the pillars of creation. So the pillars of creation are a stellar nursery in the Milky Way. This is a cloud of dust and gas, and there are stars forming inside. When we look at it with Hubble, we mostly just see the dust and gas, which is very pretty. But if we want to know what's going on inside, we can then go and take an image in the infrared. And as you can see, now we're actually peering through the dust. We can see what's going on inside. So this gives us an entirely new window into the universe and the processes that are happening. So galaxies have dust. They have a lot of dust. This is some rare galaxies, one of my favorites. This is an image from Hubble. It's just a visible light image, and you can see that there's all of this dust here blocking the light that you would not normally see, the visible light that would be coming at you. If you want to see through that dust, you have to go to the infrared. Here's another galaxy that we look at with Hubble, over here. You can see that it's got these nice spiral arms, and there's some dust. You know, these dark patches are not just like, you're not seeing through the galaxy, they are actually dust in the way, blocking your light. When you go and look at the infrared with Spitzer, now all of this star formation that's going on in spiral arms, these red knots, now suddenly shine through the dust, and you can see it, and you can actually see where the star formation is happening in this galaxy. So this just gives us a lot more information. But there's another reason why we want redder. We're all familiar with, in our everyday lives, that waves, like sound waves, actually change depending on if the thing emitting them is coming towards you or moving away from you. So we haven't had a train yet today, which is real well. But you're all familiar with if a train's coming towards you, it's a different pitch than if it's moving away from you. And that's because the sound waves that are coming out of the train, when they move towards you, are being compressed, and when they move away from you, they're being stretched. And this results in a different sound. Light waves behave the same way, except instead of changing sound, they change color. So when an object that's emitting light comes towards you, its wavelengths are compressed, the light is compressed, and it gets bluer, because bluer is shorter wavelengths. When it's moving away from you, the wavelengths are stretched, and that means they get redder. Now, it just so happens that because the universe is expanding, almost every galaxy that we see is moving away from us. This means that all of them are having their light stretched and look a little bit redder than they would if they were just standing still. And because the expansion in the universe is actually accelerating, the farther away a galaxy is, the faster it's moving away from us. And this means that its light has been stretched the most. It is the most red. So, a galaxy that otherwise we would see it in visible light, in blue light, has its light stretched and will only pop out in redder wavelengths, or the infrared. We can see this. This is the Hubble Ultra Deep Field again. This right here, blown up over here, is one of the brightest galaxies we know. It's very pretty. But if you look above it, really nothing there. When you go to the infrared, you see this little red dot, and when you go to the mid-infrared, even redder wavelengths, you see it really pop out nicely. And that's because this galaxy, the light left it 13 billion years ago. It's one of the most distant galaxies we know. And you can only see it in the infrared. So what this means for James Webb is that if this is a timeline of the universe, Big Bang over here, now right here, which is 13.7 billion years after the Big Bang, if Hubble could see over here, and here's the ultra deep field, James Webb is going to look much farther back. It's going to be able to see the red objects that are far, far away. And because the light takes time to reach us, this means that these objects are very young. It's going to see things that are just a few hundred million years old after the Big Bang, some of the first galaxies that come into existence. So that's pretty cool. All right. So armed with all this knowledge, with our ability to look back in time with James Webb, to see into the infrared and compare it with the visible and other wavelengths, just to get all these pieces of information together, we can start to address why galaxies look the way they do. Why do they have all these funny shapes, and how do they change? Well, one thing we think is that when you take these nice star-forming spiral galaxies, something happens. They become these red, dead, elliptical galaxies. But you'll notice that they don't. It's not just that the star formation that's happening there stopped, because then it would just be a red spiral. There would be no star formation. But where did you lose all your structure? Why did it become this round thing with stars just not arranged in spiral arms? Well, we don't really know. We got some ideas, but a miracle occurs. So this is one of the things we want to look at with James Webb, and one of the things we're going to do is we're going to look at other galaxies that don't fit very nicely into our elliptical and spiral, characterizations. So we've got really young blue galaxies. Remember, blue means a lot of star formation. This galaxy doesn't have any discernible shape. It's just kind of crazy and star forming. We don't know what's going on there. We got galaxies that are coming together. You can it's hard to see on the projector, but there's material here. So these two galaxies are going to merge together. And then this is the galaxy part. And then all this red stuff is material being blown out of the galaxy by something. A black hole, some kind of other violent process, something. So a lot of stuff happens to galaxies. And we usually think of space as being really, really empty. But galaxies are actually very social creatures. Most of them live in groups of a few galaxies. The Milky Way lives in a group. We live in a group with Andromeda and a bunch of other galaxies. And then some galaxies live in these massive galaxy clusters, which are these huge gravitational groups of galaxies. Well, I shouldn't use the word group again. Huge gravitationally bound clusters of galaxies, hundreds and hundreds of them that are all living in the same spot. And it turns out when galaxies live close to each other, stuff happens. Sometimes you fight with your neighbors. And if a galaxy lives in a cluster like this, clusters are not very empty. They have stuff in between the galaxies, debris. So when a galaxy is moving through the cluster, it's more like a boat moving through water than just moving through nothing. So it leaves a wake. So this is one of my favorite pictures. This is a galaxy right here. And all of this galaxy is moving through this cluster. And all of this blue stuff here is gas. It's being stripped off the galaxy because it's moving through the galaxy cluster. And all the stuff that's in between the galaxies and the galaxy cluster. So this gas here, you might imagine, was being turned into stars, and now it's not, because it's being stripped off the galaxy. And it's huge. So, things happen to galaxies. This I just like 3 pictures, but really, galaxies merge together, and this comes in a lot of different varieties, and you can see, so these galaxies are in an early stage of the merger, so you can see that they still have the spiral structure. But then what's going on over here? This is a later stage of the merger, and you can see that all of this spiral structure is just being lost in this merger. So maybe that's one of the things that happens to galaxies. So what's James Webb actually going to look at? Well, we are going to look at a lot of different things, but this is one of my favorites. This is a galaxy merger. This is stepping to 10. There are 5 galaxies in here somewhere. There's 2 merging together, all the red things. The blue stuff here, again, is this gas that's being heated by the merger, because when 2 galaxies slam into each other, it generates a lot of energy. And that energy goes into the gas, and stuff gets ripped off the galaxies, and you get tidal tails and all sorts of stuff, and all the gas is shock heated, and when it's heated, it emits in the infrared. So what we see, and this is what you guys see, this is what I see, when we break up the light into different wavelengths, we see all these spikes. All these spikes are different kinds of hydrogen, so different transitions of hydrogen, and they're being shock heated by the merger. And when we look at the different spikes and how strong they are, we can tell things about what's happening during the merger and what it's going to end up looking like. But not everything that happens to galaxies happens from other galaxies or things that are outside the galaxy. Galaxies are forming stars, which we all know results in supernova, which is a violent process. And galaxies also have black holes. We think that black holes are everywhere, but they're also annoyingly shy. They try to hide behind dust if it's there, and sometimes they even pretend to be certain kinds of stars. So sometimes it's obvious. This is M87. This is the galaxy right here. This is a huge jet that is being blown out by the black hole. It's very obvious. There's nothing else that can do that except a black hole because there's no galaxies to merge with, there's no nothing. So we know that there's a black hole in there that's blowing out this jet, and it's just this huge, massive monster of a thing in the galaxy. Over here we have ARC 220, and I don't know, is there a black hole in there? You tell me. Probably? We think so? But we can't see it because it's hiding behind a bunch of dust. So what we're going to do is we're going to look past that dust like we did with the Pillars of Creation with James Webb, and in about an hour we can tell if there's a black hole hiding in there and in lots of other galaxies. So we're going to be able to find them all. The first step to understanding black holes is just to find them, and then we're going to be able to figure out what they're doing to their host galaxies. Okay, but you know, galaxies colliding together and black holes and stuff, that's all cool. But maybe you only care about how this relates to you. Well, you're made of heavy elements and molecules. Where did those all come from? So we know that they come from stars, and stars with supernova, and we know that the first heavy elements came at the beginning of the universe when the first stars went supernova very, very quickly, very early in the universe. But what we don't know is how these heavy elements distribute themselves in galaxies. We don't know the details of how they first appeared in galaxies, where they are in the galaxies, and then eventually we want to link it back to how they form solar systems, how they form planets, how they form life. Of course, we can't see solar systems or planets very, very far away in the early universe. We can only look at the galaxies. So we want to know what the heavy elements are doing in the galaxies and how that relates to us. So, in summary, James Webb is going to be great for looking back in time, telling us how the first galaxies formed and how they change over time, what they look like, why they look like what they do, looking at galaxy collisions, figuring those out, finding all the black holes and figuring out how they're affecting their galaxies, and then also figuring out how galaxies are populated with the heavy elements that we need to form life. And I'll just end with putting it this way. Galaxies are all we're going to take a short break for questions.
So the geometry of the sun shield and the telescope suggests that we're going to be looking down and up with respect to the rest of the solar system.
Yes. Yeah. Because you need to have the sun shield in between.
One up pointed outward.
Yeah, so I don't know exactly the geometry of why the telescope can't tilt up. It can point to the solar system depending on where they are, but it only tilts up. So we have a range of view, and it doesn't include just a small part of the gap. You can't look straight up. And I think that maximizes what you can see. If you pointed it straight up, then you would see. So the question is, one side of JWST is really hot and one side is really cold. Does that cause rotation? I don't know that it causes rotation. There is radiation pressure from the sun, and the telescope has propellants that shoots out, to adjust where it's pointing and micro-adjust to put it back into orbit, pointing where it wants to be. And I'm sure that's wrapped up in there. I don't know that you need differential something to get it to rotate. I don't think rotating is going to be a problem, but it will get pushed. Any other questions?
Are you able to adjust the secondary gear like you can with crush base radio?
So the secondary gear is always, it's always directing the light back into the instruments. So in that sense, it has to be fixed. Is there a question back there? Yeah, so the question was, are any of the instruments good for observing nearby exoplanets? That is the entire next part of the talk. Any other questions?
Well, one of the things that's made Hubble kind of so popular with the public is all the stunning kind of real-time, false color but realistic looking images. Since that uses infrared, will you be able to release kind of images that are similar that'll really blow people's brains?
Yeah. So the question is basically, will James Webb be releasing images like Hubble released? And the answer is yes. Yeah, so we already do that. If you go and you look at the different image archives, Spitzer has a large archive. And Spitzer is the same wavelength. So we'll be doing a similar thing. Yeah, it's going to be spectacular, but it'll be false color because it's in the infrared.
But so are a lot of Hubbles.
Yeah.
Cool, thank you.
Any last questions? All right, then we're going to hear about exoplanets. Let's go
Hello. So I'm Jonathan.
Sorry, I don't want to tip so
This is one of the coolest videos I've ever seen. This video is of Venus